You're watching PanBlast's Compressed Air Treatment and Dust Control Systems training video. In this video, we will review equipment that will prepare compressed air for abrasive blasting by reducing its humidity or moisture content, and also equipment that will filter airborne dust from abrasive blasting prior to venting exhaust air into the atmosphere. Compressed air supply. For dry abrasive blasting, compressed air is the key medium which supplies the energy and force necessary for this surface preparation process. This is normally supplied by a main air compressor and is shown in the illustration as a yellow compressor. The breathing air compressor shown in blue as a separate unit is optional because breathing air can also be obtained from the main air compressor by additional three-stage filtration to convert standard compressed air from the main air compressor into breathing air quality, as explained in the operator protection training video. A moisture separator is normally installed as standard to remove any residual oil or moisture from the compressed air prior to use by the blast pot. However, it is important to note that this moisture separator is not adequate as a standalone filter to remove oil and moisture from the compressed air supply for abrasive blasting. Additional upstream equipment at the main air compressor is required. Compressed air quality. ISO 8573.1 was developed in 1991 by ISO, International Organization for Standardization, to help plant engineers specify desired compressed air quality globally by providing quality classes for solid particulates, humidity, and oil. Quality classes provide engineers with an internationally accepted unit of measure. A typical pharmaceutical plant, for example, would have a compressed air specification of ISO Quality Class 1.2.1. This is equivalent to 0.1 micron particulate filtration, minus 40 degrees Fahrenheit, minus 40 degrees Celsius dew point, and 0.008 ppm, 0.01 milligrams per cubic meter oil filtration. Why do we need compressed air treatment? Because ambient air contains contaminants that are drawn into the compressor. These contaminants are compressed and intensified and find their way into the compressed air system. Contaminants are also introduced into the compressed air stream by the compressor, receiver tank, piping, and other installed components. There are three different forms in which contaminants exist: solids, dirt, dust, pipe scale, compressor wear particles; liquids, aerosols, oil and water; gases, vapor; water, oil, hydrocarbons; carbon monoxide, chemical pollutants. Compressed air applications range from shop air to breathing air, with a wide range of applications in between. Let's review some key terms via this compressed air treatment glossary. Pressure dew point. Temperature at which water will begin to condense out of air at a given pressure. To ensure that no liquid water is present, the pressure dew point must be less than the lowest temperature to which the compressed air will be exposed. Aftercooler. Heat exchanger for cooling air discharged from air compressors. Can be either water-cooled or air-cooled and driven by an electric or air motor. Air-oil separator. A device in the compressor that separates oil from the air-oil mixture compressed on the air side. Drain traps. Collect and discharge liquids from aftercoolers, separators, receivers, dryers, filters, and drip legs. Dryers. Remove moisture from compressed air. Refrigerated dryers cool air to remove moisture by using a refrigeration cycle. Desiccant dryers reduce dew point by flowing wet air through desiccant beads. Deliquescent dryers reduce dew point through chemical reaction of air with desiccant tablets. Compressed air treatment levels. This table illustrates various treatment levels possible for various compressed air applications. Unless the compressor has been purchased specifically for an application-specific purpose and factory-fitted with filtration equipment, most commercial or shop air compressors are rated at Level 1 filtration and do not have an ISO 8753.1 classification. Most will be fitted with a filtered centrifugal separator that removes all solids 3 microns and larger, and also removes suspended liquids, 99% of water droplets and 40% of oil aerosols. Additional equipment need to be fitted to get higher quality compressed air, ranging from levels 2 through 5 for specific industry applications, or level 6 for breathing grade air, which is separately covered in the operator protection training video. Panblast's range of equipment are suitable for compressed air treatment to level 2, ISO 8753.1 class 2.4.4, for sandblasting use, and to level 3, ISO 8753.1 class 1.4.2 for paint spraying and powder coating applications. Compressed air treatment equipment. Moisture in compressed air is a big problem. It makes the abrasive in the blast machine damp or wet, causing the abrasive flow from the machine to be uneven and reduce or even completely block media flow. The operator may open the abrasive metering valve further to get more abrasive supply, thus wasting the abrasives. Moist abrasive media can adhere to the internal component of blast equipment, and when it dries, it can be extremely difficult to remove. Water and oil vapors can also cause flash rusting on the surface of steel products, and oil vapors deposited on surfaces will cause paint and other coatings to adhere poorly or create early failures such as chipping and separating. For those of us in high humidity areas, the aggravations created by moisture are compounded. Relative humidity is the percentage of water vapor in the atmosphere in relation to the amount required to completely saturate it at the same temperature. As air gets hotter, it expands and can hold more moisture. When air at 100% humidity is cooled by nature or man-made mechanical devices, the water vapor changes to small water droplets. In order to remove moisture from compressed air for blast cleaning, it has to be cooled by some means so drops of water can form and be removed. This illustration shows two additional pieces of equipment fitted to the main air compressor: an air-driven aftercooler and a desiccant air dryer. The aftercooler reduces the temperature of the air discharged from the main air compressor to within 6 to 11 degrees Celsius, 11 to 20 degrees Fahrenheit of ambient temperature, and removes approximately 60 to 80% of the compressed air's moisture content. This cooled compressed air is then fed into the desiccant air dryer for final moisture removal, and the dry compressed air is then fed into the blast pot's compressed air supply port, which normally has a moisture separator fitted. Air-driven aftercooler. Usually the first line of defense against the onslaught of moisture is an aftercooler. There are two types, air-cooled and water-cooled. An air-cooled aftercooler looks like the radiator on your car. All it does is run the compressed air through its tubes, while air is blown across the tubes by a fan. If sized appropriately, this will cool the compressed air to within 20 degrees Fahrenheit, 11.1 degrees Celsius or less of the ambient air temperature. So if your room is 85 degrees Fahrenheit, 29.4 degrees Celsius, an air-cooled aftercooler will cool the compressed air to 105 degrees Fahrenheit, 40.5 degrees Celsius. A water-cooled aftercooler uses water instead of air to cool the compressed air inside. The temperature of the water will determine how much you can cool the compressed air. To size an aftercooler, one has to refer to a performance table, such as the one shown on this slide. Two models are shown, one rated at 725 CFM and another at 400 CFM. If you have a closer look at the table, these CFM flow ratings are based on a 15 degrees Fahrenheit, 8.3 degrees Celsius approach temperature and inlet temperature of 250 degrees Fahrenheit or 121 degrees Celsius. These figures are approximately in the middle of the performance table and are used to rate the aftercooler and give it a model designation. However, to get actual aftercooler performance under different inlet temperature conditions, which is usually the output air temperature of the main air compressor, and target air cooler output temperature, which is the approach temperature plus the ambient air temperature, it is necessary to refer to such a performance table and not simply select equipment based on the aftercooler's model designation. Naturally, with a slower CFM airflow rate through the aftercooler, we have better heat exchange and also more moisture removal from the compressed air. Because the approach temperature can never be zero, it can also be surmised the target air cooler output temperature can never equal the ambient temperature. Hence, an aftercooler can never remove moisture 100%, and the compressed air output from the aftercooler at temperatures below the air cooler output temperature will be fully saturated. Because of this reason, it is highly recommended to have an air dryer after the aftercooler to remove remaining moisture from the compressed air and reduce the dew point from the air cooler output temperature to a target temperature sufficiently below ambient or working temperature so condensation does not occur during abrasive blasting or coating operations. Pan Blast has a full range of air-driven aftercoolers with flow rates ranging from 250 CFM to 3000 CFM to suit most application requirements. Air dryer types. Dryers are machines that dry compressed air so much that they actually lower the dew point. There are a few different types, but the main ones are refrigerated, desiccant and deliquescent dryers. Refrigeration dryers employ two heat exchangers, one for air-to-air and one for air-to-refrigeration. The compressors used in this type of dryer are usually of the hermetic type and require refrigerant gases such as R22 and R404A to operate. The goal of having two heat exchangers is that the cold outgoing air cools down the hot incoming air and reduces the size of compressor required. At the same time, the increase in the temperature of outgoing air prevents recondensation. Some manufacturers produce cycling dryers. These store a cold mass that cools the air when the compressor is off. When the refrigeration compressor runs, the large mass takes much longer to cool, so the compressor runs longer and stays off longer. Commonly, a coalescing pre-filter is installed immediately upstream of a refrigerated dryer to remove lubricating oil and other contaminants that have the potential to foul the dryer's heat exchangers. A refrigerated dryer delivers a dew point not lower than approximately 35 degrees Fahrenheit, 2 degrees Celsius. The term desiccant dryer refers to a broad class of dryers. Other terms commonly used are regenerative dryer and twin tower dryer, and to a lesser extent, adsorption dryer. The compressed air is passed through a pressure vessel with two towers filled with a media such as activated alumina, silica gel, molecular sieve, or other desiccant material. This desiccant material attracts the water from the compressed air via adsorption. As the water clings to the desiccant bed becomes saturated. The dryer is timed to switch towers based on a standard timing cycle. Once this cycle completes, some compressed air from the system is used to purge the saturated desiccant bed by simply blowing the water that has adhered to the desiccant off. The regeneration of the desiccant vessel can be done using three different methods. 1. Heatless pressure swing drying, which uses part of the dry compressed air coming from the other vessel to dry the desiccant in the vessel being regenerated at lower pressure. 2. Heated dryer, which uses a hot air blower, so there is no loss of compressed air. 3. Heat of compression, which can only be used with an oil-free compressor. A regenerative desiccant dryer typically delivers a dew point of between -40 degrees Fahrenheit, -40 degrees Celsius, and -100 degrees Fahrenheit, -73 degrees Celsius. Pan Blast's FlexiDry compressed air dryer is a heatless pressure swing type regenerative desiccant dryer. Unlike conventional systems using fixed-volume steel pressure vessels for each dryer size, the revolutionary FlexiDry is a modular plug-and-play system that can be configured for flow rates ranging from 270 CFM to 4130 CFM using various combinations of two standard flow module sizes, Flexi 4U 275 CFM and Flexi 6U 410 CFM. Assembled modules are constructed from lightweight extruded aluminium and housed within a structural steel frame for component protection and ease of transportation. Each Flexi 4U module consists of 4 vertical tubes filled with desiccant, while the Flexi 6U module consists of 6 vertical tubes also filled with desiccant. Because of the regenerative element of this style of dryer, modules are always assembled in pairs or multiples of pairs, so one set of modules can perform the drying function while the other set of modules can undergo the regenerative cycle. For example, a pair of Flexi 4U modules will contain 8 vertical tubes filled with desiccant, but only 4 tubes will be performing drying, while the other 4 tubes will be undergoing desiccant regeneration in an alternating fashion. This pair of Flexi 4U modules is the smallest FlexiDry configuration with a 275 CFM flow rate. To get the FlexiDry model shown in this slide, we require 2 sets of Flexi 6U module pairs for a total of 24 vertical tubes. Each pair is rated at 410 CFM for a total flow rating of 820 CFM. In this 820 CFM model, we will have two sets of 12 vertical tubes connected together via gang manifolds at the ends, with each set of 12 tubes alternating between desiccant regeneration and compressed air moisture adsorption, with sequencing controlled by a process controller housed in the control panel. System operation is either via 110 to 240 volts AC mains or rechargeable 12 volts DC battery supply. A Deliquescent dryer typically consists of a pressure vessel filled with a hygroscopic medium that absorbs water vapor. The medium gradually dissolves or deliquesces to form a solution at the base of the pressure vessel. The liquid must be regularly drained from the vessel and new medium must be added. The medium is usually in tablet or briquette form. Deliquescent dryers have no moving parts and don't require electrical power for operation. The performance of a deliquescent dryer, as measured by outlet dew point, is highly dependent on the temperature of the air or gas being processed, with cooler temperatures resulting in better performance. A deliquescent dryer delivers a dew point suppression that fluctuates with air temperature. Typically, this suppression is 20 degrees Fahrenheit, 11.1 degrees Celsius below the compressed air temperature. Panblast's DS series of Deliquescent air dryers feature a combination air-driven aftercooler mounted on top of a single-tank pressure vessel housing the Deliquescent desiccant material. Both items are mounted within a convenient steel frame for easy transport and component protection. Standard dryer sizes ranging from 250 to 2,500 CFM and can be optionally fitted with a coalescing filter, a high-flow moisture separator and filled with deliquescent media. Let's now move on to dehumidifying systems, which efficiently removes moisture and provide a stable working environment for blast and/or paint rooms under all climatic conditions. With the aftercooler and air dryer, we were focused on removing moisture from the compressed air supply to both abrasive blasting and coating systems. But with a dehumidifier, the focus is on providing a stable and predictable working environment within an enclosed blast or paint room for all seasons, and regardless of external weather conditions and relative humidity. There are a few methods for controlling the conditions so that moisture does not condense on a workpiece surface. One is to heat the workpiece being painted so that the surface temperature stays at least 3 degrees Celsius above the dew point. While this is usually okay for small objects where heaters could be used, it becomes very expensive to do the same for large surfaces such as the inside of a blasting room, oil storage tank, or inside of a ship tank. There is a second method, which is to heat the air within the area. However, this is only around 50% efficient and also not practical to heat the area in some climates, and while still maintaining overall comfort for the operators. A third and proven method is to use a dehumidification system for the blast and/or paint room. A dehumidification system works to reduce the amount of moisture in the air and lowers the dew point temperature, thereby preventing moisture from condensing on the workpiece and reduces the rate of corrosion on the workpiece surface. When running ducting for dehumidifier units to the chamber, the best position for dehumidified air feed return into the chamber is at the highest point of the chamber, and at the opposite end of the suction inlet, which should be at the lowest point of the chamber, just behind the paint arrestor pads. This layout creates a diagonal airflow across the chamber that gives good quality ventilation and air turns. Panblast has 4 standard sizes of dehumidifier units: 6,000 cubic meters per hour, 3,530 CFM, 9,000 cubic meters per hour, 5,925 CFM, 12,000 cubic meters per hour, 7,060 CFM, and 18,000 cubic meters per hour, 10,590 CFM. As a rule of thumb, the dehumidifier unit is sized based on the number of air changes required, and this is the volume of the chamber multiplied by 2 to 3 times, depending on room insulation and ceiling. For example, for a chamber of dimensions 30 meters length by 15 meters wide by 8 meters high, we have a volume of 3,600 cubic meters. Multiplying this volume 3,600 by 3 gives us 10,800 cubic meters per hour. Hence, the closest suitable model is the 12,000 cubic meters per hour dehumidifier unit. For a more precise sizing of any dehumidifier application, Contact a PanBlast technical professional with the following information: chamber dimensions with electrical voltage and frequency required, maximum, minimum temperature and relative humidity range in the country of installation. Reverse pulse jet dust collection systems. The reverse pulse cartridge utilizes a pleated filter cartridge to separate dust from the airstream prior to exhausting it to atmosphere. Filter cartridges are highly efficient, 99.98% on particulate as small as 0.5 microns and long-lasting. During the process of separating dust from good abrasive, a dust cake builds up on the external surface of the cartridge. If not removed, the cartridge will eventually block up completely and airflow will cease. Removal of the dust is achieved by injecting a pulse of compressed air into the center of the cartridge. This cleaning process is normally controlled by a pulse sequencing timer. Removed dust is then collected in a storage bin for disposal. An electrically driven fan mounted to the top of the dust collector generates the necessary ventilation airflow. For an operator to have adequate visibility during blasting, the blast chamber must be well ventilated. A dust collector should be ducted to the blast chamber at the opposite end of the inlet air plenums to provide the required ventilation air crossflow for removal for airborne dust and fine abrasive media. To size the ventilation dust collector, calculate the cross-sectional area of the blast chamber in square feet. Next, multiply this figure by flow factor of 30 for use with metallic abrasives, or flow factor 45 for use with non-metallic abrasives to get the required dust collector CFM flow rate. Add 10% to the required flow rate if the blast room system will be used by more than one blast operator. It is also important to note that single-use expendable abrasive media such as copper slag, crushed glass or silica sand should never be used in a blast room system due to dust overloading from the high abrasive breakdown rates. PanBlast standard dust collector sizes include 3000 CFM, 4500 CFM, 5000 CFM, 5500 CFM, 7500 CFM, 9000 CFM, 10,000 CFM, 12,000 CFM, 15,000 CFM, 20,000 CFM, and 30,000 CFM. If an application is in between standard sizes, it's better to upsize to the next available size for improved operator visibility. Similar to blast chambers, dust collectors can also be customized to suit applications that cannot use standard dust collector designs. As an example, let's size a 5 meter wide by 5 meter high by 10 meter long blast room that will be used with glass beads, a non-metallic abrasive. The cross-sectional area will be 5 times 5 equaling 25 square meters, or 269 square feet. Multiplying this by 45 gives us 12,109 CFM, so we can select the standard 12,000 CFM unit as the ventilation dust collector for this chamber size. PanBlast also has a range of portable dust collectors in the form of the VTS series, which work in the same way as fixed-type permanent mount dust collectors and are ideal for use in the field to provide ventilation for portable blasting or painting enclosures. The VTS series comes in 3 standard sizes: 5,000 cubic meters per hour, 2,943 CFM, 9,000 cubic meters per hour, 5,297 CFM, and 18,000 cubic meters per hour, 10,594 CFM. This brings us to the end of this video. We hope you've enjoyed viewing it, and for those of you pursuing silver or gold level certifications, we wish you the best of luck for the online test.